Okay, so in this video, I want to get to the math of the bias variance trade-off, and to show that the expected test error is the variance plus the bias square plus the variance of the irreducible error. In the previous video lecture, we showed that the expected value of the test MSE can be written as the irreducible error, which is the variance of epsilon 0, plus the expected value of the difference between the estimate and the function itself. Now I want to show that this part can itself be broken down into two other pieces, the bias and the variance. And in order to do that, I use a trick. The trick is to add and subtract inside a constant, and that constant happens to be the expected value of f hat. Since it is the expected value of something, it is a constant. So we subtract the constant, we add a constant, we square it, and then we have f hat minus ef hat squared ef hat minus f squared plus 2 times f minus e times ef hat minus f. Now what is this? This is f hat minus e of f hat squared expected value, which is the variance of f hat. This is the expected value of f hat minus f, which is a bias. And it's non-random, so the expected value here doesn't play a role, so it's just a bias squared. Finally, we have the cross product. Now, pay attention at this. F hat minus f expected value. Once you take the expected value, it's not random anymore, it's a constant. So we can take it out of the expectation, and what remains is the expected value of f hat minus the expected value of the expected value of f hat, which is 0. Because this becomes the expected value of f hat minus the expected value of f hat, so 0. So we showed that the cross term is 0 and we're done. So we decomposed this performance into the irreducible error, bias square, variance. Now, conceptually, what this means, especially in relationship to the R code example that you saw in the previous video lecture, is the simple to complex, moving from simple to complex. In this graph, we have 3 curves. Yellow is test MSE. This is the bias, and pink is the variance. As we increase the complexity, as the model changes from being rigid to being flexible, the bias reduces. As we increase the complexity, as we go from rigid to flexible model, the variance increases, because a model that is flexible might be too flexible, so it happens to model the variability in the data as opposed to the pattern, the structure, the statistical significant relationship in the data. So as we increase the complexity, the variance increases. Now the test MSE is the sum of the bias plus the variance plus a constant and the test MSE, as we move from rigid to flexible, reduces. As we move from rigid to flexible, the model becomes flexible enough to capture the complicated real-life phenomena. But if we turn that model more too flexible, then instead of capturing complicated real-life phenomena, it starts capturing the variability and the noise, and that's why the test MSE increases.